In this video we'll be looking at equations of lines and planes. So let me start with lines. Imagine in a 3D coordinate system you have a line running through some point. Let's call this the position vector of this point, let's call it R0, with components x0, y0 and z0. And let's say that the direction of the line is given by a vector v, little v, with components a, b and c. So R0 gives you a point on the line. This is your line L, and V gives you the direction of the line. With these data you can actually formulate an equation for any point on the line. It's a parametric equation, meaning that there is a parameter in there. So it basically tells you, well, to get to any other point on the line, to Q with coordinates x, y and z, basically what you have to do is start from the origin, follow the position vector R0, and then take some multiple of the direction vector v and add it to that to get there. And that's true for any other point on the line. So for any point on the line, you can get the position vector pointing, let's call it R, the position vector pointing to any point on the line depends on a parameter t, and it's basically the position vector to p and then some multiple of the direction vector v. So t here is a parameter, it's a arbitrary real number which will give you points on the line as t runs along the number line. This vector will basically sweep out the entire line that we have there. Okay, so of course you could turn this vectorial equation into coordinate equations. So you could say that x is equal to x0 plus a times t, y is equal to y0 plus b times t, and z is equal to z0 plus c times t. Okay, so you can either use the vector form or this scalar form with 3 components or 3 coordinates. Okay, pause the video and input your answer below. Okay, I hope you paused it and have found that well, one possibility to complete this set of equations is just simply have the coordinates of p as these numbers 5, 1 and 3, and add to that multiples of t, where the multiples are given by the components of the direction vector. So that's 5 plus 1t, 1 plus 4t, and 3 plus minus 2t, so that I could even write as 3 minus 2t. Okay, so this would be an equation for the line that passes through that point in the direction of the vector v. Okay, So next we go and talk about planes. So the equation of a plane, the equation of the plane, we again need some initial data. Imagine that there is a plane in space. For that, what we need is a point on the plane. So that would be, well, let me call that P again. So a point on the plane. It has a position vector from the origin pointing to P. And the other piece of data that we need is a vector that is perpendicular to the plane. It's called the normal vector, and we'll give it again components A, B, and C. Okay, so it is perpendicular to the plane itself. So with this data, what we can actually see is that if you pick any point on the plane Q, connect it to P, what you will notice is that this vector that is PQ is going to be perpendicular to, it's going to lie in the plane, so it's going to be perpendicular to N, the normal vector. So it's true that PQ for any point Q in the plane is going to be perpendicular to N, meaning that their dot product is going to be 0, while PQ can be expressed as the sum of the position vector that goes from the origin to P and the position vector that points to Q. So this could be written as as the difference of R and R naught. So that difference is PQ. And with that, we have the equation. Now, if I write that in components, if this position vector has components x, y, and z, then this equation, using the dot product, turns into A times x minus x naught plus B times y minus y naught plus C times z minus z naught equals 0, where x naught, y naught, and z naught are the coordinates of that given point P on the plane. Okay, so that's the equation for our plane. Let's call it S. So for the plane S, we have this equation. So my next question is for you to give me the equation of the plane, an equation of the plane which passes through the point with coordinates 2, 4, minus 1 and has a normal vector with components 2, 3, 4. Okay, so pause the video and give the equation of the plane below. I hope you paused it and you used this formula to simply say that it's 2 times x minus 2 plus 3 times y minus 4 plus 4 times z minus 1, so that's a plus 1 equals 0. You can of course expand to get 2x plus 3y plus 4z and then collect the constants. Minus 4 minus 12, that's minus 16, plus 4, that's minus 12 equals 0. So that's the equation of our plane that passes through P and has a normal vector n. Okay, So with that, we can actually finish. I hope you enjoyed this video, and I'll see you in the next one.